Hello everyone, this is Mix K. In this video, I'm going to go over the little note catcher paper in the last page of our packets. Now, if you are in one of my college level classes, this will be on page 15 and 16 of your packet. If you're in one of my Goddard or honors level classes, this will be on page 19 or 20 in your packet. So same pages, just slightly different page numbers, but last page of your packet either way. So first off, we're going to skip the can crush for right now. We're going to come back to it. But I want us to talk first about our Boyles Law activity. So in our Boyles Law activity, we had a syringe. Okay, we capped it. It had a plunger that we push in and out. And inside of it, we had a marshmallow. Now what we notice is that when we pushed in on the plunger, and I'm going to abbreviate marshmallow as MM to save me some space, the marshmallow got smaller. When we pulled out, it got bigger. So this is showing us Boyles Law. So in Boyles Law, when pressure increases, volume decreases because we are pushing our particles closer. Okay. And when we pulled out on the syringe, we decreased the pressure, so the volume went up. Okay, so the particles got further apart. Now, another examples of Boyles Law that we saw, oops, sorry, I'm knocking stuff over, was our textbook activity. So in the textbook activity, we had wooden blocks with a syringe in between them, and we started adding textbooks to the top of our syringe. Now, every time we added a textbook, the syringe started moving down. So as we added books, the syringe went down. So this is another example of as we increase pressure, volume decreases. And something else that we notice is that volume decreased less and less each time. Eventually, there's going to be no more extra space between the particles, so we're going to not be able to make it go any smaller. So we can see this relationship in our can crush. So in our can crush, we saw the volume get smaller in that experiment. So I'm going to write that in the can crush, the volume went down, but I'm going to put a little thing that the pressure went up. I'm going to write it really small for a minute. Okay, we don't need to write anything here right now. Now, when we started looking at temperature, we saw something else. So we had our Boyles Law lab where we had a flask that was hot, and we flipped it into cold water, cold, hot. And what we saw happen is the water started filling the flask. So we went from hot to cold, which means our temperature decreased. And what we saw was that the volume of space the air took up went down. The water pushed up into the flask. So our volume of our gas got smaller. We went from taking up the whole flask to taking up part of the flask. So as temperature decreases, volume decreases because our particles get closer. Now there's another part to this. As temperature goes down, the pressure inside also goes down because the particles slow down and hit the sides less. So here's the key thing here. In our flask, we have the pressure outside from the air on the outside of the flask, and we have the pressure inside the flask. Now the pressure inside got smaller, it went down. So these started off as being equal. Now if this got smaller, the pressure outside is now greater. And that pressure outside is what's pushing our gas up and into the flask. Now if we think about this with our can crush, in our can crush, we also had temperature decrease and volume decrease. And we noticed that the can got squished. So something about the pressure inside was less than the pressure outside. So let's put these pieces together and talk about our can crush. So in our can crush, we had a hot can. We flipped it into our cold water, and the can crushed. Okay, so we hot can flipped into cold water, can crushed. So the big thing that we changed here was temperature. Our temperature went down. And we saw that the volume of the can went down because those particles are closer together. So those particles are close together, they take up less space. But there's something else going on here. We also need to think about the fact that when the temperature goes down, the pressure goes down because the particles move slow and hit less. So if we think about that can, when we flipped it into the water, okay, the pressure inside went down because the temperature went down. So now the pressure inside is less than the pressure, I don't need to write that, I can just write P, pressure outside. So that pressure outside literally squishes our can. That pressure outside is so much greater than the pressure inside that it squishes the can. Air outside crushes the can. Now if we flip our paper over, we had a couple more, but for these ones we don't need to worry about the can crush, so we can cross this out. So our other Boyles Law lab is we still had a beaker, but this time it was hot, and we flipped a cold flask in. And this time what we noticed was bubbles came out of the flask. So we went from cold to hot, and bubbles came out. So here we had our temperature increase. It went from cold to hot. And this time we saw that the volume increased. The particles move further apart. Now the other thing here is about the pressure. This time the pressure outside is less than the pressure inside. And we know this because we can see the gas getting pushed out of the flask. So in this one, when temperature increases, pressure also increases because the particles move fast and hit more. More hits, more pressure. Now for this one, the Avogadro's Law one, we looked at a flask and we put water and Alka-Seltzer in there and it started to bubble. But what we did was we sealed it with a balloon and we saw that the balloon filled with the new gas. Whew, my hand's getting sore. Okay, so that balloon filled with the new gas. So this time we made more particles, so they took up more space. More particles take up more space. So if we flip this, the opposite is also true. Less particles take up less space. Now in this one, our balloon was flexible, so it was able to expand. Now in this next one, we used a rigid container, a container that was hard. And we used this film canister, and in that film canister, we sealed it up with water and Alka-Seltzer inside. And what we noticed was that after we let it sit, it exploded. It popped. Okay, so Alka-Seltzer produced gas and it exploded. So in this one, we saw that as we add more particles, our pressure increases. More particles, more hits, more pressure. The opposite is also true. If we decrease the number of particles, our pressure will decrease. Less particles, less hits. Now, this last part we are doing on the computer, and we're looking at the relationship between all of these different values. So we're going to see, how do particles change as we change pressure, volume, temperature, and number of particles. Now, just to finish off this paper, we're going to write down two equations. The first one is for comparing how a sample of gas changes. So if I change the temperature, I can figure out some information about how it's going to change. So this first one is called the combined gas law, and it's better from when you're comparing how a gas is changing from one state to another. The other one is the ideal gas law, and it is better for when you are missing a piece of information about your gas. So if I had all my information except for temperature, I can solve for temperature. Here, though, I'm looking at how it's changing. So if I start with my gas in one form and I heat it up, I change that temperature, I can figure out what the pressure or the volume is going to be. Awesome. So if you are missing anything from these pages, please make sure you get them down into your packet. And I hope this helped, and have a wonderful day.